So thank you for joining this presentation. I will introduce and kind of discuss some things about our project number 35, which is about managing inconsistent development artifacts. So just to introduce us, because now we are all hidden behind those back screens all the time, and those icons with just saying your initials. So this is us, the researchers from MDH involved in this project, and these are the partners. So we are working with Saab, Bosch, and Tetra Pak in the project. And as you see, there is space to join for other companies, but of course only if your logo is a nice circle so that it fits the scheme. So just kidding. So in this presentation, I will give a high-level overview of the project and discuss some high-level principles and research setup. And then after this is all kind of high-level stuff. I will discuss in a bit more technical detail a case study that we've been working on in the past sprint. And after that, I will give some overview of plans that we want to continue work on in the next sprint as well. So let's start by the kind of explaining a bit better the title. So we are talking about managing inconsistent development artifacts, and to be a bit less generic than artifacts, let's look at two examples. Let's say we're looking at software or system models and implementation. So this is code, software code, or software models from which then code is generated. So this is the thing with software engineering, that of course we can have this partial or automatic generation of code from these models, or they are implemented manually. And we see in our partners that this model-based development is adopted to enhance or to raise the abstraction level, and thereby make it easier to reason about the software and so on. And what we then see is that in this whole theme that we have talked about in the keynotes of today as well, is to become to go towards a more kind of continuous development, so to do more faster iterations on all of these artifacts. So both on the side of the models and the side of the code are they're iteratively developed and so on. And then this problem of inconsistency kind of emerges when the models are developed frequently, and they are kind of core development artifacts, meaning that the code that is eventually created should be in line with those models that are created. And what we then see is, or this inconsistency problem kind of emerges when those things are iterated over lots of times, because yeah, if you update one and not the other, somehow some inconsistency will occur, so they might contradict each other. And then if you build on top of this kind of introduced inconsistencies, you might end up in even more trouble later on. So to link this more clearly to this continuous development, let me just introduce in one slide how I see this, these different phases of continuous integration and so on. So we start with continuous integration, in which we are frequently integrating the models and the code, so all our artifacts, into some shared repository. And then in the next step is continuous delivery, where also we make a release available of this. Then there's the continuous deployment, where you also deploy this on target devices running this software. And then to complete this DevOps kind of cycle, you can also get the data from monitoring the devices in operation, and then feedback that information back into the development. In the companies where we are working with, we have mostly focused on the things that can be controlled kind of in-house, as was also discussed in this keynote by the Siemens Healthineers. It's about controlling things that you can do still in-house. And so we focus mostly on continuous integration. And then in the context of this model-based development that I've been talking about. Because when we look at classical model-based development, people always see this kind of V model with kind of well-gated different steps and kind of fairly long processes between them and so on. And then we are saying, why can't we do kind of quicker iterations on these kind of bottom boxes, where each of them is iterated or each of them is frequently iterated, and we are building a more continuous model-based development. So when we are thinking about this, back to the title of managing inconsistent development artifacts, I've shown now this kind of introduction of model-based development, and I kept it at very high level. So there's lots of different practices that that kind of fit this kind of model-based development description. And then you can see that there are also, following that, there are a lot of these kind of scenarios of artifact synchronization that we can think of. So in the example before, maybe it was closest related to consistency between the intended architecture described in some kind of models and the implementation described in code or even also in models. And then another kind of artifact synchronization stuff is when we are looking in completely different settings, where models are used in, let's say, a product line setting to describe different variants of the same system. And then when those models are partially reused across different variants, then you might end up also in cases where they should be synchronized, because you want to, for example, share the changes that happen in the platform to derived products as well. And then yet another kind of different setting is when we are talking about models from which, for example, code is generated, and then that generated code is a bit modified in special cases. And then you want to kind of complete this this round trip back to the model. So these are all kind of different ways of explaining artifact synchronization, and in particular model and code synchronization, which is what we are looking at. And this is something that is a kind of challenging thing, especially in this, when you're doing more continuous integration and continuous development. So I think this is a nice kind of additional aspect to these research challenges that Miroslav introduced in this general session just before lunch. So the aim of our project, kind of high level, is to define best practices and formulate design principles, and in general kind of work towards a general framework for identifying and visualizing these inconsistencies between development artifacts, and then in all these different settings, of course. So that was the very fast introduction to the kind of high level overview of the project, and I want to just briefly run over some of the high level principles and the research setup that we have in the project. So I've been talking about this model-based development and this more continuous development, and so the longest version of that story is included in this thesis, Advancing Continuous Model-Based Development in Industries. This is my licentiate thesis, and in the footnote there's a link to the presentation if you're interested in this. And what we discuss there mostly is going from this idea of introducing continuous integration and so on in model-based development, what the effect of that is on model synchronization, and what kind of tasks you should do in order to do model synchronization. And we study two completely different settings of model synchronization and provide some improvements there. And this is based on software center work in previous sprints. But the general principles kind of in that thesis, and also in the project now, is that we are looking for solutions that can be provide kind of insights to engineers. So they should provide traceability between parts of artifacts and so on. They should be applied as early as possible, so that as early as possible you have insights into possibly introduced inconsistencies. At the same time, they can usually not be automated. So what we found is that in the end, in the companies, you will have some kind of engineers that have to make some decisions. But we are working to make that a lot easier. of course, these approaches that we are proposing should also minimally impact existing workflows. As discussed before, there's a very complex kind of pipelines and stuff in place to develop these software. So we want to impact them in a minimal way. Something that we found is that we have to deal with artifacts at different levels of abstraction. So I've talked about models and code, but you can think about models also at very much different levels. So you can have system models that are extremely high level and just dividing some functionality across different components, and then there can be like at the lower level software models that really define how to implement something, or define the structure and behavior of those components. And overall, and this is also kind of an overall thing, these solutions need to be lightweight in use and for especially maintenance, because of course the situations in which we are working, nothing of this is static. So these models are modified all the time. The code is modified all the time, and so if we're providing some framework or some solutions to this consistency checking, also that itself should be probably subject to a lot of maintenance and so on. So we want to make that as easy as possible. So to just zoom out a bit and show it in a bit more of a picture, what I see it like this. We are working on trying to define these kind of principles for, let's say, continuous model-based development, and then in particular, artifact synchronization. And we are evaluating those results in different use cases in the industry. And then, of course, those use cases are also kind of feeding back into those principles. So if we put the university, let's say the research side on the principle development, then of course we are going also to that other side, to those companies to do those case studies and get some interesting data. And so in the projects we are working in case studies with all of these companies, but now I will go into only one of them because we don't have time to discuss all of them. So I will discuss in detail one use case of model synchronization that we have been working on in the last 6 months. Okay, so now we have left the high level stuff and we're going a bit more into technical detail. But I'm trying to keep the slides at very much the level of picture so that hopefully you can still follow. What we will talk about is a model that is defined in some kind of domain-specific tool, which we are configuring parameters and variables and so on, such that we are creating a program that will eventually run on a PLC. Of course, we cannot directly execute that model, but there is a step in between where we are generating the code that is then deployed on the model. And you can already see that this is related to this continuous development parts, where of course, when we are updating all the time this model, in reality, we probably will not be able to deploy all the time on this PLC. But at some point, you want to again have a synchronization between this PLC and the model, such that you know what is actually running and such that you can do proper maintenance to the software. And I will now make the picture a lot more complicated to show that this is not so easy to accomplish. So when the generated code is deployed on the PLC, what also happens is that some kind of common libraries are loaded onto the PLC such that you obtain a program that you can actually execute. And then you can imagine that this model is created once and then reused in a lot of times. But in some of these occasions, there's a need for kind of customizations of that. So in kind of special factory settings, you want to customize them, this code. And this is done manually, let's say on site. Some engineer modifies directly the code that is running on the PLC. But this information is not present in the model. So now we can start seeing this problem where we are making these changes on site on the PLC, and therefore now it's no longer in sync with the model. And when we want to do some maintenance or some updates, bug fixes, whatever, we no longer know exactly what is running on this PLC. So we have to somehow get back out of what is running on the PLC, we want to construct again back the model that we have used as input. And to do that, the first step is to export a program from the PLC. And what now is exactly the problem is that this exported program and the representation in the tool, this model in the domain-specific tool, are now inconsistent because of the changes that are made by the on-site engineer. And the question is, how can we synchronize these things? How can we bring back the changes that are made on-site from this exported program and put them back into this model in the domain-specific tool? So this is one of these settings of model synchronization that I've been talking about. How do we synchronize these two representations of the same thing? It's a model, and there has been code generated from it, but now they have become out of sync due to these manual changes. How can we synchronize them? So to do that, let's take this figure and isolate the kind of important parts that we will be looking at. So what we will look at is the exported program and the generated code. Can we synchronize these two? Because when we can synchronize these two, then we can also bring back the changes to the model. Because we need to identify what has changed on the level of from the generated code to the exported program before we can propagate that back to the model, of course. So what we will do is we will take these two and try to create the difference between these two. And this solution now the solution gets a bit more technical because these files are under the hood. Let's say they are XML files, can be very large, describing the logic that is executed and the other data that is defined to make that logic actually execute. So I will try to explain this with apples. The problem is that, as you know, you cannot compare apples and oranges. Actually, in Dutch, you cannot compare apples and pears. But okay, we will keep to apples and oranges. But in this situation, it's actually a bit worse than that. So I wanted to illustrate that we can't just compare apples and not to oranges, but actually we are trying to compare apples to a very exotic fruit basket with a lot of stuff. And all of this stuff we don't actually need. So we need to somehow prune away this stuff. And so the first step that we want to do is we want to get rid of information that is introduced by the code generation step, by the exporting from the PLC step, and by this loading of the libraries. So what we do as a first step is to create a kind of domain-specific pruner. And this sounds maybe very specific, but actually it's a very general solution because we can make these pruners based on what we know that is present in the files, and therefore we can create this in a very nice automated way where we can kind of read in these library files, let's say, and then based on that build a pruner that will get rid of all of those things. And I will illustrate that in the next step, because actually this is not enough yet. Because what we get out of it, even though in the file 1 prime, so this generated code is still apples. So now we have a bit fewer apples because maybe there were some apples added by the code generation that we don't need. And 2 prime is now, we have gotten rid now of the exotic stuff, but still there are some aspects of these apples. Some, like in XML terms, there are some types of nodes or types of attributes that are new. So let's say here's the leaves on these apples that we don't have them in the generated code. And the idea is that if we have information that we don't have in the generated code, then it cannot be interesting to propagate back either, because apparently this information doesn't exist in the generated code. So then we don't want to bother people with looking at these changes because apparently they're not relevant. Okay, so now to get from this kind of apples with leaves and stuff to kind of clean the apples where you have exactly two of the same things to compare, what we do is again a very generic thing. So taking this file 1, which is exported from the code generator, we get the XSD of that. It means the schema of the XML. So this is a file that defines what type of nodes are in the XML and what is the exact hierarchy of that. So file 1a is the XSD, the schema of that of the XML file that is file 1. Then we have defined a higher order transformation. This is the HOT circle. That together with 1a in step C generates a transformation. And what it does especially is this transformation 1b that is created is supposed to take any file and keep only those types of nodes that it knows about. And these types of nodes that it knows about are coming from 1a. So this 1b, eventually it will, when you run this on a file, let's do it on file 2 prime, we will get out of 2 prime only those things, the type of things that we know about in file number 1. So we'll only keep stuff that is in the generated code and we'll get rid of everything else. So this is what is done in step D. So we are pruning away everything else and we are left with kind of, now we can finally compare apples to apples. So we are finally at the level of apples and apples, and we should remember that we were coming from a very exotic fruit basket. So we have really reduced and formed this in a good way, and now we can try to compare these two baskets, 1 prime and 2 double prime, and see, okay, maybe there are some of these yellow apples that have been added, or there's some other differences. But we can now finally properly compare them. So we had to set up this entire framework just to be able to properly get the difference between these two programs. Now what we can do is to do this comparison, and we will end up with this file number 5, which is a file containing the differences between the two files. And this is the point what we have done, all of this we have done so far. And now we'll talk about what we are working on now and what we'll do also in the future. Which is that from this differences file, what we want to do is want to allow engineers, again, this is kind of coming back to these general principles where fully automated backpropagation is probably not ideal. So you want to have some human in the loop to decide which things should and should not be propagated. So what we want to do is allow them to choose what differences should be propagated back and what differences should maybe not be propagated back. And the ideal situation is, of course, that in file number 5 now, it only shows those differences that have been made by these manual modifications on site. And then of those modifications, the engineers back at the office, let's say, can decide which of those changes should go back to the general model and which ones should not. So this is the stuff that we are working on. And the good thing about this generic framework before it is, one, that it is very generic, so you can run it on, well, let's say any type of for all these kind of PLCs or for any program. So we try to do very diverse input, and it creates the correct kind of pruning steps in the whole process. And the other thing is that the human in the loop, let's say, that has to decide which of those changes should be propagated back, has to or doesn't have to wade through a lot of these false positives. So don't have to go through all of these exotic fruits, these bananas and kiwis and whatever. We are only looking at changes to apples. So that concludes the kind of detailed case study. Yeah, I hope that it was a bit understandable. I can imagine that there was a kind of big slide building up, so might lost a bit. And now to end with, I just wanted to highlight some plans for the next sprint. So what we will be working on in general, it's again these kind of general principles, and then doing the case studies at the companies. In terms of the work towards the general principles, what we will also be doing is a systematic mapping study of kind of inter-artifact synchronization approaches, where especially we will emphasize on existing tool support and industrial adoption to see which types of things are really in use. And then what we want to do is focus on this model and code synchronization. So even though we have called the project Artefacts, inconsistent artifacts, just as a generic name to not all the time have to say model and code or something, but we are very interested in this model and code synchronization. And of course, the underlying idea, as introduced before, is to allow for more continuous integration, for more continuous development when using also software and system models kind of inside this continuous development loops. So this is on the general principle side. And then on the case study side, we will continue working with Bosch and Saab and Tetra Pak on the case studies that we already have established at their with them. And maybe we will do some new case studies in case you have some interesting interesting use case for us to look at. So that was all I wanted to talk to you about. And thank you for your attention. If you have any questions, I think we have time now. And otherwise, please send me an email on this address. Thanks.